sure.
Fantastic. Well, Professor Kambhampati, you've been doing a lot of really interesting work in the planning space over a number of years. And more recently, I think you've had some very interesting commentary about the ability of large language models to reason and to plan. But I'd like to go back in time a little bit to where it all began. So before we started thinking about all these questions, how did you get into AI in the first place?
Yeah, that's funny. So as an undergrad, actually, I did a bachelor's thesis on speech recognition. So isolated word speech recognition using LPC coefficients and Capstral coefficients, etc. Somewhere here is my undergrad thing, which was actually typed with handwritten diagrams, etc. That was back in 1983. So that was sort of my original connection. And I actually remember when I was an undergrad then, DARPA SIR, which is the DARPA speech understanding project, was like a big thing. And so I was sort of reading about it as part of my work. And I mean, so I was working with this professor called Narayana, who's a speech processing, signal processing guy. I mean, speech has actually been always a signal processing community thing. I did my undergrad in electrical. And so I remember this DARPA speech understanding thing, which looked a lot more interesting than just, understanding speech as against just recognizing individual words, which looks like more of a signal processing task. And so that's sort of my foray, I guess, entry into AI. So that's when I got started. And of course, I mean, it's in general, the doing full-on understanding of speech, I guess we only have come somewhat closer to it, a lot more closer to it now than, of course, then, but,
Sure.
It took quite a while, yeah.
So beginning from speech then, how did you end up getting interested in planning?
That's another interesting thing. So I was at Maryland. In fact, I think I actually came to CMU and I was in signal processing. And then I shifted to Maryland, transferred to grad school there. I was in Vision Lab for a while. And then it was the time when I suddenly again got interested in machine learning. But in that particular time, the machine learning was actually explanation-based learning, which is sort of not too many people are aware of now. It's the idea that if you have a theory and you can provide a proof as to why an example has the correct label dog, or example has the label it has. So that sort of the explanation allows you to figure out which features are relevant in effect. And so that sort of explanation-based learning can be thought of as a feature selection-ish perspective. And so I remember that I got interested in that. And then I slowly did a thesis actually in plan reuse and case-based planning-ish connection. So that wound up being my PhD thesis. My master's thesis actually was in mobile robot path planning, quadtree-based mobile robot path planning, multi-resolution path planning. So those are the ways I got into the planning. And again, the connection between planning and learning is something that always fascinated me, because even the plan reuse was because it's a primitive form of learning. Essentially, you are actually using old plans. And when you mentioned the LLM planning stuff, one of the things that we are making connections to is you can actually think of LLMs as providing a different way of doing case-based planning, where LLM constructs the case on demand based on your prompt, and then you are correcting it using planning techniques. But we'll get to that later.
Yeah, there's a lot of interesting intersections to get into with that. One thing you just brought up that really interested me was the idea of explanation in determining feature relevance and doing feature selection. And I think that there's maybe a full circle kind of deal we've seen here when it comes to earlier on. A lot of feature selection and machine learning was, people developing intuitions, doing things a little bit more manually. And then a lot of people liked the idea of deep neural networks because it's like, well, I don't have to do all this manual feature selection and things are a bit more efficient. But then we come full circle to, well, now I don't understand what is going on and I need to explain things to myself again. And I'm curious how, when you were first getting into just machine learning in general, sort of what that looked like, because I think that at this point probably we hadn't entered the deep learning decade yet, but there were still people working on this.
So this was very beginnings. In fact, I think I could have. I was planning to go to the second machine learning workshop, which then finally became the ICML conference later on. And so there were some people like Rizard Bikalski who were doing like basically what you would now call supervised learning. But there was this very significant interest both by Tom Mitchell and Gerald DeYoung. Those are the two groups who looked at if you have a background knowledge and you explain why a concept has the label it has, it significantly helps in actually basically generalizes. So if I were to tell you that this is, I mean, the example they use is cup, and if you say that this is a cup, and then what makes it a cup? Basically, you'll say a cup requires the ability to hold something, and you should be able to hold it. And that's the theory. And then you prove that the example that I have in front of that I showed you actually has the ability to hold something, and you holding it. And that generalizes that single example into a bunch of other cups which have approximate configuration like that. And so it's basically explanation-based generalization where, figuring out that not all pixels of the cup are important for it being called cup, right? For example, if you change the color of the cup, it's still a cup. And if you kind of put a couple of dents, it's still a cup. Whereas if it doesn't have a bottom, it's not a cup. And this is something that machine learning always wondered as to, where do you go from this single example? And we tend to do this. I mean, there's actually psychological results showing that part of the reason we do single example or few example learning, few shot learning that has become called in the context of an LLM, is because we are very quickly able to explain to ourselves why the label was given to that thing. And then that explanation sort of guides us. If you kind of reduce the number of features or the attributes of the thing that are relevant for its class, then you have, in a sense, generalized it. And that's basically how it was being seen. Explanations were being seen. And then, of course, they had to think in terms of what is a background knowledge with respect to which you're proving that this thing is a cup, etc. And at that time, they used to look at logical theories. So there would be like a first-order logic theory of what makes some general thing a cup. And then there is a proof that this instance in front of me is actually, satisfies that theory. And whatever aspects of this instance took part in the proof, those are the pieces that actually are relevant to its cupness, right? If I never use the color aspect of the cup in proving that it's a cup, then color doesn't matter. So that's basically the whole point of explanation-based learning in general. Now, the interesting thing is, as you mentioned, after that, they moved on to when things like neural networks came, the second coming of neural networks, not the first coming, which was 62 when I was born, but the second coming when, again, people got interested in neural networks. There was this worry that, neural networks might actually give you the correct classification, but you are it's not clear to you whether they're looking at the same thing or something else. I mean, you may just be intersecting on the training set, but the generalizations are very, very different, which is what much later now we talk of the school bus ostrich example, where, it basically sees the school bus with a little extra noise and sees it as an ostrich. It's the same thing,
Yes.
It's not enough to just say that we seem to agree on the training examples. So they worried about it and they wanted an explanation to some extent. And so one of the earlier things was actually trying to reconvert a neural network, a learned neural network, into a rule-based classifier so that people can have a sense of what the network is doing. And so you first learn the neural network and then you convert it back into sort of a rule-based or logical form. Variations of that are still existing even now, because when you, and that version, I think of it as interpretability. I mean, a poor man's version, a poor woman's version of interpretability is saliency regions, where if you just have, pixels and then you kind of shade some of the pixels and say, these pixels, these regions seem to be more relevant in the class of the thing being bus, then you kind of will say, okay, these are probably relevant, but it's a very broad brush, and it doesn't work all the time. So my usual challenge to people is show me a saliency region-based explanation of that adversarial school bus that becomes an ostrich for many neural networks. It will show a bunch of pixels that are disconnected because those wound up playing the most important role, but they don't give you any more insight as to why the machine is seeing an ostrich where you are seeing a school bus. So that sort of brings up this whole issue of common vocabulary between you and the machine. And more of my later work, in fact, in the last 10, 15 years has been, last 10 years at least, has been this whole, I have this explanation-based, explainable human-AI interaction, which has been my work about there. The explanation says, I am trying to explain my decisions. The AI system, I'm trying to explain my decisions to you, the human, in terms that make sense to you, as again as just soliloquizing myself and then saying, look at my saliency region and be impressed. So in some sense, providing explanation actually requires mental modeling. You need to sort of understand the other person, how the other agent in the loop is looking at the world, what are they expecting about the task. And this is true for even single examples, and it becomes even bigger issue if I'm trying to explain my behavior. A behavior is not a single short example, it's like a video of my life. And it's very hard to do saliency regions on videos. Right? Because, and that basically becomes extremely hard for us. And so in some sense, actually, you can think of human-human interaction had to deal with that, because eventually you have a neural network of some sort, not the kind that we currently use, but some sort, and I have a neural network of some sort, and yet we are able to communicate, and we're able to communicate in this multi-modal thing where in particular we have these symbolic concepts that we are using to reduce the amount of bandwidth that is needed to actually talk about the saliency region of the video. So for example, if you ask, why did you take this flight as against this other flight in coming to my city? The easiest way is a symbolic explanation. The hardest way is to provide a video of my life and point out pieces and say, this is the saliency region. Do you understand? And that, because that one is such a time-consuming thing that in a weird way, I tend to think that we had to invent language to communicate with each other. And because the language winds up becoming a symbolic means of communication between two agents who are doing sub-symbolic reasoning, sub-symbolic, view of the world. And it's the same thing that happens, that's what we are doing, but that also is what machines have to do for working with us. And I think saliency region-based interpretability, for example, is bad from my perspective because it makes the humans do the heavy lifting. And I want the machine to do the heavy lifting. If you want, the machine should make sense, should do the heavy lifting of making itself explicable or interpretable to me, as again as it's saying, okay, look, here is the huge big transcript of my decision process, or the pixels that were kind of more relevant, and you figure out what is important, whether or not I'm looking at the world the same way you're looking at. So all of these are sort of connected. At that particular time, the explanations wound up becoming a way of doing it in the very beginnings. Now you essentially again have some, in some sense, in a most recent work that we do, we essentially say that symbols have to become a lingua franca between AI systems and humans, even if in fact the AI system is not doing symbolic reasoning by itself. It needs to translate its communication to the humans in the only form they understand, which is kind of closer to symbolic. Basically language is already symbolic, and logical reasoning would be also symbolic. And so it almost needs to reach its decision. And then when you ask, why did you make this particular action as against this other action, that explanation would have to be in a local symbolic model that it winds up learning. And so that's actually one of my, several papers in the last couple of years about both. There's a Blue Sky paper in IIII 2021, I believe, on symbols as a lingua franca between humans and machines. And there's also papers thought of, there's a iClear paper last year as well as another one this year, which sort of look at how machines can automatically learn these symbolic models on demand, just to make sense to you. So it's sort of explanation is a customized action. So the way I explain to you may well be different from the way I explain something to somebody else, because it depends on their models of the task.
Yes.
And so that winds up, making your decision, but explaining it in terms that others understand. And in the case of neural, networks, which are basically looking at the sub-symbolic level, like pixels and signals, they still need to learn a local symbolic model that they would use to communicate with the humans, because the humans would be asking questions in that symbolic level. And the grounding as well as learning of the model should be done by the machine. It should do the heavy lifting, not the humans. And that was, one of the big things that we've been pushing.
There's a lot in what you just said. And I think that this connects to a number of different conversations I've had. I can think of, for example, Bean Kim, whom I spoke to quite a while ago.
Bean Kim, I actually completely understand. We communicate a lot. So certainly that's one of the things. So yeah, just because you brought it up, one of my examples essentially is, think about that infamous 33rd move by AlphaGo. Okay.
Yes, right.
The Go experts, I actually don't play Go, but the Go experts say, oh my God, how did it make this? Why would it make sense? Well, it makes sense. The system did win. What exactly are they unhappy about? They're unhappy because they can't explain. Now, if the explanation is that, look, the proof is in the pudding, it won. So what do you want more from us? That's not what we expect as explanation. The explanation should be something slightly symbolic. It's sort of a compact representation that will help us realize what other similar situation would this kind of a surprising move be again relevant. And the reason people are surprised at, the experts are surprised at, is there is no vocabulary item that humans have that corresponds to a compact representation of the kind of the board configurations under which this kind of a move is a reasonable thing. Like, for example, in chess is full of moves, concept like castling or, checkmate, etc. These are concepts that you have to develop. The 33rd move, the concept vocabulary didn't even exist for the humans. And so that's actually the more interesting case where, to understand what the machine is doing, we may well expand our vocabulary with the machine, and you working together. This is actually one of the challenges we talk about in the Blue Sky paper and symbols as lingua franca. So one aspect is the humans kind of providing the concepts they already understand, and the machine converts whatever it is doing into those concepts. The other aspect is it actually needs to help the human come up with new concepts, so that now we'll start calling this thing this name, and then it becomes essentially a symbolic explanation. And so yeah, that very much is relevant to the kind of work that we do. The interpretability ultimately cannot just be sort of showing videos with shading or showing pictures with shading, because that's just a very poor quality thing. And so you almost, even if the machine doesn't think in symbolic terms, it needs to convert its reasoning back into symbolic terms while talking to the humans, because that's the best way to conveying. And the irony of this is rich, because then after it gives the symbolic explanation, you may very well be converting it into some symbolic ways in trying to make sense of it in your neural network. But your conscious brain essentially still is happy that it got a symbolic explanation. So when neural link actually happens, maybe we don't need language and we don't need to talk to each other at all. But up until then, this winds up being a very relevant thing. But go ahead.
How do you think about what this realization of new concepts might look like? I'm thinking specifically of, you brought up earlier the ideas of analogy and grounding. And I think often when we consider the definitions of new concepts, the way we learn new things, that is often by analogy to things we already know. If we put it in perhaps Stefan Harnad's language, it's not like I can just have some free-floating signifier that has nothing to do with anything I've encountered in my life, but it, by analogy, kind of grounds out into something I've encountered in my own experience. And so in your symbols as lingua franca work and in this development of new concepts between machines and humans, I'm curious, about how you think about that playing out.
So first of all, let me start by making the clear-cut point that most of the symbols as lingua franca is actually machines dealing with the terms that humans already have grounding for, and the machines don't have grounding for. And so they basically, there's like they learn the grounding once and they can start using that language. It's like, I mean, English is my second language. And so I had to figure out the words that, native speakers use, and then they already use them. I didn't need to teach them these new words. And then I just need to use the words they have, and I have to ground them so that I know, even if in fact, actually, as an undergrad, which we were talking about earlier, as an IIT student, I went to IIT Madras as a guy who could only speak Telugu, which was my mother tongue. I couldn't speak English. And I almost remember at that time, in this pseudo-psychological way, when somebody asked me some question in English, I consciously translated into Telugu, make the answer back into Telugu, and then translate it back into English. Now I don't see that anymore because it just happens as I'm talking to you. But, that was something that was very much, I could sense that was happening because that was like English was a second language for me. But I'm just translating my reasoning into terms you understand. In the case of machines, they're translating their reasoning into terms that humans understand. So the human language already exists. That is like the biggest part of the work, actually. But the second part that's even more open-ended is this AlphaGo thing, where coming up with new concepts, it's actually obviously a lot more interesting, but doesn't happen often. I mean, in most of the time, you don't, if you're not careful, you can make up, you get into this whole Alice in the Wonderland thing that when, I can just make up a word and, expect it to mean what I want it to mean. That you shouldn't do that too often, because then essentially, again, it actually gets in the way of interaction with the person. So in terms of, mostly I'm using the language that people already have grounded in their heads. I the machine have to learn the grounding and then be able to translate. That's like big part of the thing. And every once in a while, I might actually have to come up with the new concepts. And that is the question that you're asking as to, how exactly would this happen? This is all we can at this point say is sort of an interactive development, interactive exercise between the machine and the human, in terms of saying, what sort of, let's make this word which sort of corresponds to this particular board configuration, and in the case of Go, for example. But I mean, I would say that's still less often the case. Most of the time, humans already have a language and you're trying to use the language. It's instead of just saying, why don't you understand my internal representation, of me, the AI system. And since we're here, I want to also mention one important difference. Actually, the whole neuro-symbolic has become a big deal. Everybody talks about it. And, they're like two very different ways of looking at neuro-symbolic. There's one set of people who essentially think that internal reasoning that AI systems do somehow has to have symbolic components to it. That means there's an abstractions that they are building up from the pixels and the signals. They're building up symbolic abstractions and reasoning over the abstractions. The symbols become just abstractions and the raw signals. That could be, that could improve their efficiency for sure. But the abstractions that the machines develop, there is no reason that they would correspond to the abstractions that we have developed. It's actually very interesting that we all develop similar abstractions. I don't quite know how to explain that, probably because we are brought up by other humans, from get-go. But machines, if they develop abstractions, there's no guarantee. It might improve their efficiency, but there's no guarantee at all that they would then be able to, then we will be able to understand them. The other is the version that I'm talking to you, which is, I don't care which language you think in, or if you even use any language. I mean, if you want to talk to me, talk my language. And my sense, my strong research bias is in the human AI interaction. Machines should do the heavy lifting, because I hate the world where I already have trouble dealing with other people and trying to make sense of what they are thinking, etc. If I now have to also figure out the internal representations of machines, it seems like AI has failed, as again, has succeeded in making our lives simpler. And So in fact, in the old days, like NASA would have these planning systems, and they will try to talk about this mixed initiative planning, where if the planner is making a mistake, the human in the loop will try to improve its performance. But that would involve the human going into the search queue of the planner. This large, big search queue that is maintaining that search queue data structure, rearranging things, etc. These are people who basically gave up on life because they're being paid for doing this really sad work. That is not what human AI interaction should be. Human AI interaction should be AI systems doing the heavy lifting in converting the reasoning, irrespective of which language they did it in, which basis they did it in. At the time of explanations, they convert it into some local symbolic models. And the example I typically give is, if for example, some of your listeners might be familiar with LIME, which is one of these explanation systems on the saliency reasoning thing, right? So LIME essentially computed local linear models, and it would provide explanations in terms of the local linear models. All I'm saying is, we, in the ICLAIR paper last year, we compute local symbolic models. We learn local symbolic models and explain the decision in the context of that local symbolic model. And that's basically, we do that because the symbolic model, the terms, the predicates that are used in that model are the things we already know humans understand, because that's a shared vocabulary. We had learned the grounding, and we are learning the model as needed. And over a period of time, you might wind up getting a big enough model that winds up being like a symbolic persona between the machine and the human. And so that's basically the kind of neurosymbolic reasoning that I'm specifically talking about, where I don't really care what the machine is thinking and what it's doing its reasoning in terms of, as long as it makes sense to me in my terms. And so it has to kind of develop a symbolic persona. One of the very interesting questions, philosophical questions that we actually bring up is it possibly could be that humans have started this way when they developed the language, but then we have come to a point where we basically think in language. I mean, it's like, to the extent you're consciously aware, you essentially almost think as if you are your language. And so even though we start by saying that machines essentially can do whatever kind of reasoning, but they just need to be able to communicate with us in the language we understand. What happens in the asymptotic sense when the machines might very well say, it's just my symbolic front becomes me, as against my symbolic front just being a front. I only really right now want a symbolic front, but, and that to me leaves everybody happy, in the sense neural network based deep reinforcement learning systems is what you are interested in developing, you could, right? And if they are only working somewhere on Mars and they don't need to explain their decisions to any human anywhere, it doesn't matter how they came up with that reasoning. But if they need to make, then they need to be able to translate it at that time. As again as saying, we now have to change our reasoning process because humans only tend to talk in symbols. You can do reasoning any which way, just translate it.
Yeah, what you just said about thinking and language is really interesting for a multitude of reasons. And recently I spoke with a linguist named Ted Gibson, who really, I think as you were talking about earlier, says and claims that language is primarily for communication, and contra Chomsky, that it is not used in complicated thought of other types. And he references a study by Ed Fedorenko's lab that showed when humans engage in different types of complex mental tasks. So for example, thinking about music or doing mathematical reasoning, the language part of their brain actually does not seem to light up at all. And of course, I think a lot more studies need to be done to come to a complete conclusion here. But what's really interesting about that is when I did some additional reflection, yes, I think intuitively, it does feel like I often speak to myself in language. I have this internal monologue, and I think that's what you were referencing earlier. But actually, I guess not everybody has an internal monologue. And B, I think when you become sufficiently fluent at doing something like music, for instance, you kind of stop using the crutch of language to articulate to yourself, okay, this is what this note means or something. And it becomes a lot more fluid.
Yeah, I completely agree. And I think honestly, actually, that is what, first of all, I think So this issue of conscious versus subconscious mental, activity in humans in particular, again, I'm not a neuroscientist, I'm not a psychologist, but, obviously like dabbled on things. And so certainly we basically, the conscious veneer that you put is only a very small part of the subconscious stuff that goes under the hood. And that's a very relevant point. But it's equally relevant that we needed that conscious veneer, certainly for interaction. And to the extent you needed to have an internal monologue about, if I do this, will it work, kind of a thing, you will quickly find that the subconscious part is sort of, it's more like model free rather than model based in the RL terms. And so an abstract version, which is actually symbolic, is probably what you would wind up using either to communicate with people or to actually tell yourself. I mean, I find it fascinating. So first of all, there's this brings up this big distinction that I've always been talking about in my work, about tacit versus explicit knowledge tasks. Many things, of the many things we do, a subset of them we can not only do, we can talk about how we do them. That is the explicit knowledge tasks. And most of the other things we do and we have no clue how we do. Those are the tacit knowledge tasks. So if you think of, I would almost say that of the things that humans do, it may very well be that 80% of it is tacit knowledge based and 20% is explicit knowledge based. But this percentages change quite significantly if you talk about human civilization, because even if in fact human civilization is just the tip of the evolutionary iceberg, it's completely based on explicit knowledge and codification of knowledge, etc. There's nothing to write if all you're talking about is how to walk, etc., and you can't actually explain what you're doing. So much of human civilization is very much based on this explicit knowledge tasks. The interesting part is the explicit knowledge parts are very important for interaction between us. We talk to each other. I mean, sometimes I can do demonstration, but there are only so many things I can do demonstration. I mean, there are many more things that the language can be seen as sort of a constraint over the what I call space-time signal tubes. And so by saying that I took this flight as against this flight because I had this other wedding to attend, in your mind, you have constructed huge number effectively of potential paths that I had. All of them share these constraints. And I didn't have to tell you the specific video of my life that happened. And this becomes very important. This became very important to us with respect to interaction. And it's been so useful for us as a civilizational matter that I'm actually always fascinated by the fact that we take things like very tacit knowledge tasks, such as like basketball, right? And you would be talking about very symbolic terms in symbolic terms to describe basketball. If you only understand the basketball game reviews by the sports writer, you can't play it. But on the other hand, the fact that you have these sorts of interesting concepts, and I'm actually thinking of this one particular concept that which is actually a complex concept, but it's like a single word. Hopefully it'll come back to me in a minute. But those concepts you actually make up for even tacit knowledge tasks. It's the same thing for music. You're completely right that an expert musician is not actually thinking specifically in explicit knowledge terms. It sort of comes like they basically are doing it as if it's a skill. But then if they need to simulate where they are going with it, or they're trying to explain it to people, they need to use symbolic terms. And that is actually kind of fascinating to me, that despite most of the things that we do being tacit, we actually wound up developing language, which is very much about explicit knowledge tasks. And the funny part is the way we do the language parsing itself is tacit, but it actually talks about the domains of expertise, which are very much explicit knowledge tasks. And one of my laments has been that the old AI was focusing completely on explicit knowledge tasks. If you, in fact, want to make a very nice distinction, the GoFi, what people tend to call GoFi, focused on explicit knowledge tasks, for which the models can be written by humans. Remember, the models would not be learned, it would be written by humans. And humans
Yes.
can't write models, that they basically don't have explicit knowledge tasks. So there would be, but the new AI, in essence, also works for tacit knowledge tasks, of course, because you're just learning rather than starting from human given models. But there has been a temptation to convert even explicit knowledge tasks into tacit knowledge approaches. And that means, don't tell me, I'll just watch, how you do things and try to figure out what is the company culture, which is actually can get you into all sorts of trouble, because that's where the machine might miss, there are things that I can actually tell you. And, we should be able to combine both explicit and tacit knowledge tasks, and they have, competing advantages and complementary advantages. And we should be able to use both of them. That was that's one of the things that used to fall through the cracks. The funny thing is LLMs have changed the equation. LLMs, I consider LLMs as like a gray, in a weird way, like a revenge of, the whole idea of everything being seen as tacit knowledge, I used to call it Polanyi's revenge, because Polanyi was this philosopher who was worried that science mostly thinks about explicit knowledge tasks. Human civilization thinks about explicit knowledge tasks rather than tacit ones. And in AI, people call this Moravec's paradox, because Moravec said the same thing, but Polanyi said it a lot before him. But the point is, the revenge part happened between 2006 and I guess 2013 to last couple of years back, when we converted everything into tacit knowledge tasks. And even though they're actually explicit, because we don't want to talk to people, we don't want to take what the humans are saying, we only want examples. But one of the funny things that's happening with LLMs in the scene is they've been trained essentially on symbolic knowledge, because language, if you especially talk about normal language models like the ChatGPT, they're trained on the symbolic models of basically the word models of the world. And then so they can be used, you can actually almost tease out approximate symbolic models of the tasks that you are trying to solve. And I tend to think of many of these new developments that people are like enamored with, where reinforcement learning people basically are worried. Actually, some people basically use these LLMs to come up with skills, approximate skills, which then would be used to guide the simulator-based deep reinforcement learning system. That is actually a way of using symbolic knowledge to control the sub-symbolic reasoning, except here the symbolic knowledge is being teased out of LLMs instead of talking to a single person. So the joke is, if you ask a single human being, how do I do this problem, that's considered GoFi and that's considered cheating. If on the other hand, you ask the entire humanity to write everything it knows onto the web, and then you train these massive LLMs on them, and then you ask the LLM, it's not cheating, it's modern AI. And it's a very relevant way of looking at things, because it actually, human civilization, to the extent we have used tasks, etc., the way we do things is making more sense to us. And a deep reinforcement learning system, trying to learn these concepts from first principles, from pixels, etc., is both extremely slow and also likely to be kind of not sensitive to human preferences. So in fact, the iClear paper this year that we had essentially talks about how humans can give symbolic advice to machines, which then can be, which the machines can essentially interpret the right way to improve their, performance and so on. And that sort of a work, as well as there was another ICML paper last year, which also gives approximate models that improve the speed of the underlying deep reinforcement learning system. These models can be now teased out of LLMs, because LLMs are like a store of our knowledge, but not a but only in approximate form. And then if there's a human in the loop, which sort of improves it slightly, then all of a sudden, you have this ability to make much bigger, much more efficient reasoning than you could with, sticking around at the pixel level, for example.
Yeah, a lot of connections here. And I want to start to work on how this ties more explicitly to planning. And as a way of getting there, I'd like to construct some foundations first, since I think we've mostly been talking about other things. So as one potential prompt here, you gave this 2011 summer school presentation where you described sort of your complaints before and after the advent of scaling and a lot of machine learning techniques. And you asked before, what good are expressive, ambitious planning paradigms when we have so little scalability? But then your concerns about the field kind of change. So could we perhaps do a little bit of history here? Could you tell me a bit about what planning looked like before we had the scalability, and then how your feelings about the area of research kind of developed over time?
Yeah, so the point that was being made. So first of all, let's talk about a little bit of the word planning first. The word planning with a capital P and small with the planning, as the automated planning community, ICAPS community does. They are like slightly different, but they are like the capital P planning. Any sequential decision making problem is a planning problem. That means you're trying to put together a sequence of decisions. Markov decision processes essentially are like the bedrock of doing plan generation. And the question then becomes, at what level of abstraction is this MDP looking at the world? If it is looking at the atomic level or the pixel level, you tend to think in terms of deep, like basically lowest level. And the word planning and reinforcement learning, which many more people understand because of AlphaGo, etc. Reinforcement learning on a simulator is planning. Okay, because the simulator essentially is the model of the world. And the model is intractable. It's just a big model because the simulator is a very complex simulator. And you are essentially trying to figure out how to make a plan or a policy by essentially trying things out on the simulator. If you try things out on the real world, then that is the true reinforcement learning. And that nobody does, even though people say reinforcement learning. When Rich Sutton talks about reinforcement learning, he really means working on the real world in the raw in tooth and claw. The problem with that is that world is ergodic, non-ergodic. And so if you make a mistake, you die. And my joke is, if the civilization, to the extent civilization depended on reinforcement learning, it's not you who learned from your mistakes. Many a time, in some cases, the mistakes are bad enough that you would not live to see the next day. But the rest of us who are around you say, oh, that doesn't look like a smart thing to do. And so in the multi-agent setting, we learned errors that we shouldn't be doing because we saw you doing it. And otherwise, actually, if a single agent is doing reinforcement learning, it's going to basically get stuck everywhere. This is what Jan LeCun's joke about the cars trying to do real reinforcement learning in real world. They'll keep falling and then they'll not go anywhere. But when you have a simulator, which people tend to think as if it's completely like a real world, but simulators don't grow on trees. Simulators are written by humans. If you say model, people say, no, where is the model coming from? There's some human has to write the model. We don't want models. But if you say simulator, they don't ask that question. But that's a very strange thing because simulators are written by humans. Like the Microsoft Flight Simulator is written by a bunch of Microsoft Flight Simulator programmers. And any simulator thing would be written by people. It's just the difference is procedural versus declarative model. Okay. And so now if you think in terms of planning and RL, I would say RL typically has been associated with procedurally described models, that is simulators. And planning, the ICAPS community planning, for example, starting from strips, the Shaky, the robot strips, has been associated with the declarative model based. So instead of procedural model, you have a declarative model, and you're winding up doing the reasoning with that. And the distinction actually is very similar to Boolean satisfiability versus constraint satisfaction. Boolean satisfiability, you write all the constraints in actual declarative form, saying it's P or not Q or J or not M, etc. is one constraint. And there's a whole bunch of constraints like this, and you're trying to find an assignment on all the Boolean variables that satisfies all the constraints. Constraint satisfaction, on the other hand, each constraint is an opaque piece of code. You give it a partial assignment, it will tell you whether it's happy with it or not. And the issue then is coming up with a complete assignment that all the pieces of code will say we are fine with it. All the constraints, which are opaque pieces of code, are fine with it. At a certain level, they're essentially isomorphic problems. One is procedural, one is declarative. And I teach my students essentially that the reinforcement learning, simulator-based reinforcement learning and planning are exactly that way. They're very, it's sort of, they're two countries separated by a common language, common problem, essentially, like, Britain and US. So that's planning, essentially. So the question then becomes, what makes a planning problem hard? Okay, if you're thinking more in terms of the declarative models, what makes a planning problem hard? It depends on things like, is there a deterministic versus, the usual environment types that you talk about in the intro to AI. Is it a deterministic versus a stochastic environment? Is it a dynamic versus a static environment? Is it a partially observable versus fully observable environment? Is it a single agent versus multi-agent environment? And the usual question in what has been called classical planning is essentially, you can think of it as deterministic MDPs. Okay, and if you have a deterministic MDP, then you are still computing a policy, but there are much more efficient techniques for computing the policy because you can actually get a single line plan. You don't, because if in fact it's deterministic, then you will never get into the wrong states at all. You start from where you are and you go towards the goal, and so you find the whole A-star search, etc., are ways of solving deterministic MDPs. Now, once you start having things like durative actions, stochasticity, dynamism, etc., that's when the models become more and more expressive, and computing plans with guarantees becomes harder and harder, which is not surprising. For example, if you take MDPs, MDPs are polynomial in the number of atomic states and essentially either exponential or undecidable in the case of partial observability. That's at the number of states. And planning, and declarative models tend to think not in terms of atomic states, but lifted states, because you think of states in terms of the features that describe the states. And that reduces, so if you have like k features, then you have 2 power k states. And so the planning is still polynomial in these 2 power k states, but we tend to think of the input as in terms of features. And so you say it's exponential in terms of things. And so the scalability part that you are talking about is, how do we take larger and larger planning problems in terms of the number of the input size and the goals, and figure out how to generate the plan, that's like the classic planning problem. And the cost of that goes all the way from something like a very simple strips planner. Already the generation is like p-space complete, because it turns out if you have the model is essentially an action with preconditions and effects, and the preconditions and effects are essentially proposition symbols. Okay, and in that kind of a model, is expressive enough that you can write Tower of Hanoi problem in that model. And once you can write Tower of Hanoi problem in that model, you realize that it's not in class NP anymore, because Tower of Hanoi's problem with the Tower of Hanoi problem is the solution is exponentially long in terms of the input size. That's why we talk about Tower of Hanoi or Towers of Brahma. They basically about these, the priests are doing them, and when they are done, the world will end, because they'll never get done. If you have 64 disks, it will be 2 power 64 sized plan. Okay, so the plan itself becomes exponential. Plan correctness becomes exponential time to check, because it's exponentially long. And so planning becomes, complexity wise, it's p-space complete. And you go up from there. Then you go to stochastic planning or partial observability that becomes 2x space, etc., etc. And so that is the question of scalability. And I think at the back in 2011, what I was talking about is actually connected to this conundrum in AI, which is playing out in multiple places. Again, it's very relevant now too, which is actually, do you want to only look at problems that have tractable worst case computational complexity? Or do you want to look at any problem and do the best you can do, without guarantees? Did you see what I'm saying? So in fact, knowledge representation, the so-called knowledge representation, logical knowledge representation community, there was this difference between people focusing only on tractable classes of first order logic, because otherwise they're worried that inference would be too costly. But then when you make that assumption, then the actual burden is on the person who is giving you the knowledge. They now have to make sure that they no longer think in terms of any logical representations that wind up becoming intractable for you. And then there would be people, and that was called the quote unquote neat AI in my grad school days. And the scruffy AI people would say, hey, look, you let people say what they want, and you do the best you can, and you no longer give guarantees, because ultimately computational complexity doesn't go away, right? The interesting thing that has come back right now is when you think in terms of, in general, computational complexity. I mean, I have this whole thread once that I wrote it for the, I think, CSCM blog. There's a sort of a death of computational complexity, in the sense people no longer talk about they talk about guarantees. And if you don't have guarantees, then you don't need to think about if the plan doesn't have to be correct, if you just have to give a plan, then it's just a question of, you no longer have to worry about the actual complexity of finding the correct plan under those constraints. The advantage there is you let people give the problems they have in the most natural form they have, as against converting them into a form that you can give guarantees on. The disadvantage is there are no guarantees at that point. And this issue becomes hugely important when LLMs are being used to sort of do what some people think that they can do planning. And there's really no reason to think that they can do planning, because they're essentially doing approximate retrieval, they're n-gram models. They would wind up retrieving things, and it's not guaranteed to be correct. And sometimes it's correct, and when it's correct, you're happy. Whether or not it's correct is decided either by actually trying to execute it in the real world and see if you fail or succeed, or you have an external verifier, which the LLM is not its own verifier. And then that verifier tells you whether the plan is correct or not. And if you do it that way, you will very quickly see that actually LLMs are pretty bad at coming up with. They will give a guess for pretty much any highly complex, planning problem, a guess. And their guess is just as bad for the highly complex planning problem as it is for a very simple blocks-world stacking problem, because they're not doing reasoning. They're essentially retrieving from all these huge traces of human knowledge that's been there on the web. And so that winds up being, so one of the computer circle in my recent talks, I basically talk about the fact that while LLMs cannot do planning by themselves, they are great generators of ideas. They can give you a seed plan, and somebody who knows whether or not it's a correct plan can critique it and try to improve it. Outside reasoners can try to improve it. And when you can do that, essentially you can actually handle more expressive planning problems with external critiques. So the generation would be done by LLM because it's just guessing. And these critiques actually try to make sure that they're correct in different aspects, that the logistics are correct, or some durations are correct, etc. Even then, it's not a guarantee that the entire plan is correct, but at least some of the obvious ways of plan becoming wrong are removed. And if you think about it, that's pretty much what happens in Copilot. When you're writing a program, like you're basically giving the code the specification, and it gives you a piece of code, right? The thing that's actually helpful in Copilot is that you have these incremental interpreters that are built in most IDEs. And the incremental interpreter at least makes sure that the code it's generated is syntactically correct, means there's no syntactic errors. Once that is done, then all bets are off. At that point, whether or not it is actually right piece of code for you is only you in the loop who knows how to program can tell. And that's why every once in a while you will see these tweets by somebody saying, oh my God, I just spent 4 hours debugging this very devious bug in this 10-line code that Copilot gave me. But that's only once in a while. Most of the time, what it gives, when it's syntactically correct, it's also wind up being useful. So that's like the critiquing and then hoping for the best after the fact.
Yeah, there's again a lot of interesting connections here. And I think I'll maybe mention, just for somebody listening to this who heard your comment about LLMs not reasoning, the way you showed this with Blocks World was you changed the names of different objects in Blocks World, right? And you sort of maintained having the LLM produce the same sort of plan or task. And ideally, changing the names of things should not change the semantics of what it is that you're saying, but this caused the LLMs to do things significantly differently. And so that's one way of thinking about how what's going on here is, as you said, this approximate retrieval, as opposed to what we would think about as the robust kinds of reasoning that you and I are capable of doing.
Exactly. Yeah, and that's very much true. And then one very relevant comment is, it's also not the case that LLMs, so there is this other hope that people have, that even if in fact they come up with the plan that is not initially correct, they can critique the plan, that LLM can critique the plan itself. And we have basically shown very recently that actually that's not true at all. If you again do a systematic study, basically when they critique their plans, their overall performance as judged by external verifiers goes down, not goes up, but goes down. And which should not be surprising, because as I joke, if you don't know how to solve the problem, just go with your first guess. If you second guess yourself, you're more likely to be even more wrong. And most of what happens when LLMs self-critique themselves is they will walk right over accidentally correct plans, only to end with only to end with a wrong plan. And so they wind up actually having lower accuracy. Once again, the best way to use them is an external verifier or a human. And the external verifiers very much basically can do backprompting, saying this, try again, or here is a problem with the plan, try again. And that does seem to improve their accuracy quite significantly. And which is not bad, because, if you are able to get the plan after 7 tries, according to what the outside external verifier is saying, that's not bad. It's like basically playing 20 questions, right? And except whether or not you got the right answer is only known to the outsider. You can't guarantee that I just, can tell you this is the number you're thinking of, or this is the thing you're thinking of right away. You have to have the external verifier in the loop.
Right. And this speaks to, I guess, a lot of different things. And for specific examples of this, you brought up SayCan, for instance, and how this manifests in robotics. And a conversation I had with Talia Ringer, who does a lot of really interesting work on theorem proving and programming languages, brought up how this manifests in proof repair and large language models. And so when you have this external verification system for a proof generated by a language model, you can again do this kind of backprompting that you're talking about and get things sort of correct. And it's a lot more efficient to have this external verifier where the LLM can just let me generate something, and then I can immediately check it's correct and then get that feedback. And so you have this sort of, I guess, combination of I'm learning things through a bunch of language teaching me about the world and getting all of that data. But then the moment you hook up something to what you're saying, an external verifier, you also have this efficient, well, you need that kind of grounding in the real world in a sense. And then there's also a kind of efficiency of learning what's correct or not.
Yeah. So there are 2 points. I mean, I'm almost agree with you at 2 minor, two different things. One is the efficiency really is not, I mean, it's not that it's efficient for language model. Language model would be incorrect if the external verifier is not there. It is efficient for the external verifier that they have access to language model, which actually can generate ideas that are kind of likely to be true, but it can't guarantee that. And so overall system is efficient. And if the LLM isn't present, then it becomes the classic generate, test, debug approach. In fact, Marvin Minsky is famous for saying that all intelligence is pushing the test part of generate test into the generate part.
Mm.
right? And essentially, if you basically generate test is a weak method. If you can keep generating and then testing, and the tester knows the correctness, then that would be a sound method, but it is a weak, that means an inefficient method. With the LLM, the generated things are more closer to being correct, and that improves the overall system's performance. The second part, that's actually a more meta point, and we have another, there are like 3 NeurIPS papers this year. The first one talking about this whole thing about backprompting, and another one talking about a benchmark for LLMs for planning tasks, and a third one talking about how the verifier for planning to work, it actually works off of a planning model.
Mm-hmm.
And you have to ask who is giving that model. And if I could argue that one idea is that, and actually I do give you the model, and the LLM is being used as a speed up on the on the verification system, when the human is giving the model. But we also show in this NeurIPS paper that you can actually, instead of asking LLMs for the plans, first you ask it for models. That means you ask, what do you think are the preconditions for this action? What do you think are the effects for this action? So by doing this, I'm basically asking all the actions, their preconditions and effects. And normally you assume that the human experts have given it. And I'm saying that human experts can work with LLMs to improve their speed at which, their efficiency with which they can come up with these models. And once they say they're fine with the model, that can then become the one on which a verifier is working. And then it will then start doing backprompting and LLM. So in both ways, LLM can be helpful. So one of the mind-boggling things that people, I think, have a hard time figuring out is what is hard and easy for humans and what is hard and easy from a computational algorithmic sense. Both of those are very different from what is hard and easy for LLMs. Like, for example, many problems, the whole notion of complexity hierarchy and things like NP completeness come from the fact that generation is hard and verification is cheaper. Typically, NP is the class of problems where you can check in polynomial time whether the solution is correct, but there are exponential time, number of candidate solutions. That's why you wind up taking exponential time. So people tend to think it is true that for an algorithm complexity perspective, verification is cheaper. An algorithm doing verification runs faster than an algorithm doing generation because it needs to somehow do an overall search. For LLMs, on the other hand, they are just as good or bad about verification as they are about generation. There's no difference. And in fact, another way of thinking about it is they will give answers to the question in the same milliseconds, whether the question you're asking for is a simple lookup of O1 complexity or a semi-decidable problem, right? All of which they will give a answer. And in all cases, the answers are not guaranteed to be, it's not like the more complex problems are likely to have more incorrect answers. In fact, the correctness of the answers depends very much on the training data. So if in fact there is a lot more higher quality data on the bigger problems, and you are asking one of those bigger problems, they'll just regurgitate that for you, and you will be sufficiently impressed. And it's not surprising that the easy problems, in fact, day-to-day things, there tends to be a lot more conflicting information in the common crawl than about, let's say, some esoteric subject in high energy physics. Where not enough people even have the time to sit down and write misinformation about high energy physics. And so this was never part of the common crawl. And so it may actually have higher accuracy in more esoteric domains that we tend to think are only highly intelligent people can do, and can have lower accuracy on the stuff that you think anybody walking on the street should be able to do, because there's also conflicting information on that. And see, this is something that I find that people don't quite understand, because all of AI has always been anthropomorphized. We tend to anthropomorphize everything. Eliza, the original chatbot that had rule-based system, was anthropomorphized so much so that Joe Weizenbaum had to shut it down. LLMs are
Mhm.
way better than that. And so I'm not surprisingly, we anthropomorphize the heck out of them. But we need to remember that what is hard and easy for us or for our computer algorithms is not hard and the same way for them. This actually explains a whole bunch of things. It sometimes might actually be easier for an LLM to come up with a code for solving the problem
Mhm.
than to give the solution. That's not true for humans. That's not
Mhm.
true for humans. That's true for machines, because the code knowledge may well be on the GitHub. GitHub is probably not likely to have as much of conflicting data as the solution data. And
Mhm.
so it's doing approximate retrieval in both cases, and in one case the code would be from the GitHub piece, because that's what would make sense. And the other case, it's actually trying to get the solution directly. It's more likely to be wrong in the solution and less likely to be wrong on the code. And so this is exactly the kind of thing we were doing in that other piece. I was saying that I can use LLM to tease the model out, because it's no harder for it to come up with the model than to come up with the solution. And it's not any more guaranteed, but it's no harder either. That's not true for people, because typically people may not know what are the true preconditions and effects of various actions, but they might say, oh, this particular recipe will work.
Sure.
Right.
Yeah. Yeah, I guess a lot of things to kind of get into here. And I think that one thing that sticks out to me in a lot of what you just talked about and some of the examples you gave is the view you've articulated on LLMs as cognitive orthotics, essentially, rather than full-on alternatives for human intelligence, and that we want to use a sort of LLM modular architecture instead of humans in the loop or other specialized sound reasoners. And
Yeah.
I want to connect this to some of our conversations earlier about interpretability and then also about representations, in that when you are putting LLMs along with humans, other external reasoners, then of course you have this sort of language with which you have to communicate between the different systems. And as you've also pointed out, there's, in general, I think, little reason to believe that the maybe distributed representations inside an LLM or the representations inside another AI system align well with what we humans use. At the same time, for LLM specifically, and as you've noted, we can kind of communicate with them. And some people have taken this as far as calling LLMs maybe even more interpretable, because I can just ask it things and it will tell me.
No.
I remain kind of skeptical of that view, but I guess yeah.
So I think, first of all, it is indeed the case that LLMs are speaking our language. Okay, there's no question. There's no question about it. I'm actually, by the way, today, it turns out that I'm sitting in a like a workshop on AI for healthcare. And then I came out of it to talk to you. And then I have to go back to that. And then one of the funny things they were talking about, somebody was talking about how ChatGPT actually did, people, the patients like ChatGPT more than they like the doctors. Because doctors are actually trained to make sure that they are correct and they can avoid malpractice lawsuits. ChatGPT is trained to please you. It will tell you what you want to hear in the language you actually understand. Okay, so that part of the interpretability is no longer an issue. The human can, if the human is in the loop, they can see, they can understand what it is saying. They don't need to understand the internal representations of LLMs at all, because the output is in the linguistic form. The interesting part there would be essentially making sure that any formal critiques that are actually looking at this linguistic representation are essentially able to parse it. Thankfully, LLMs can actually provide multiple versions of their outputs. Because one of the things is the fact that they speak in language is, from their perspective, is like a minor thing, because language is English and code are equally natural for them, because they're essentially just predicting the next token. So you can essentially ask, give me the plan, and give me the plan also in the PDDL representation, give me the plan in the time window representation, and actually then the different critiques can then make sense of those different representations in terms of the semantic sense. The syntax part, they're happy to provide in fact, my joke about how to tell whether or not you are talking to an LLM or a human on the other side is if the person on the thing on the other side says, here is the answer, but here is a 100-word summary of it in iambic pentameter, it's not a human. Okay, because it's extremely hard, except probably for Shakespeare, to put everything in like iambic pentameter or to summarize it, it's very easy for LLMs. The change of form is something that is quite amazingly, they're quite amazingly good at. And the usual anthropomorphization problem becomes even crazier in the case of LLM because we judge each other on form rather than content. And in fact, my joke about all the grade school teachers going crazy about ChatGPT-based essays is because between you and me, they were never really reading all the essays. There are too many essays to read. They look at, is the handwriting good? Does the sentence structure look good? Is there 5-paragraph structure to the essay? Which are all syntactic characteristics. They have nothing to do with the content. And we always hoped that form and content are correlated. It was kind of always an iffy assumption to make, but it was at least there was some correlation in, for the case of humans. And that correlation has been blown to smithereens when kids are actually asking, ChatGPT to write. All of them write business prose essays, and none of them look. I mean, you can find. In fact, I was just saying this, in this medical thing, one of the doctors was saying that she uses ChatGPT to essentially double check and improve her case reports at the case notes. At the end of the day, they have to write tons and tons of these case notes, and she makes ChatGPT will help her improve the grammar, improve punctuation, all that stuff. And that's so widespread now that in some sense, a badly written piece of English is more a sign of humanity of the agent than anything else, honestly. But all of this is about form, and they can convert form into multiple different ways without ensuring. I mean, they don't ensure that the semantics will be consistent, but they will be form would be in the right form, and the critiques can then each critique can look at the form that they want and then provide criticisms. So the interpretability problem actually becomes a very interesting, different version in the context of LLMs because you speak the same language, but it's still, in fact, one of my biggest nightmares is if you think of GDPR, right? GDPR basically says, the customers, I mean, the end consumers have a right for explanations for decisions that were made that affect their life, right? The simplest way you can provide that explanation is let one system which doesn't speak, which basically does whatever random reasoning, and it basically makes the decision. And when the humans ask, LLM chatbot just gives the explanations. And the important part about explanation is the explanation really indicative of the reasoning you did, or are you telling me what I want to hear?
Exactly.
If you just put LLM, it will tell you what you want to hear, and you would be happy. And in fact, the sad part is much of human interaction is like this. If you are unhappy with something and you start, call up these complaint lines and talk to some customer service representative, they're typically trying to tell you what you want to hear, try to, cool you down and so that you won't blow up, etc. They're not actually telling you the real reason necessarily either. But we certainly don't want that kind of a thing to be done by machines also, because explanations basically are also connected to lies. Because explanations are about your mental model, and I'm trying to tell you, given your mental model, I'm trying to kind of paint a picture that would make you happy with what I am doing, even if that's not the real reason why I'm doing it. And that winds up becoming a huge issue with LLMs because they can generate the form of explanations that would be nice to people, just like they can generate the form of diagnosis that would make patients feel good. In medicine, there is this thing about medical competency and bedside manners. It's the only thing, they're both important. In fact, many people don't like doctors who don't have good bedside manners. But on the other hand, in the end, your life depends on not their bedside manners, but their actual medical competency. It's good to have bedside manners, but if two people with the same medical competency, one has better bedside manners, you're more likely to go with the other one. But if I give you one doctor who has amazing, bedside manners, but basically flunked all their tests and, pretty bad doctor, the other person, and I've seen such doctors in my life, maybe you have seen too, other doctor has bad bedside manners, but is top of the line in terms of their diagnostic abilities, that becomes a harder decision for people. And LLMs will always give you what you want to hear because they have the perfect bedside manners, because they've been trained to essentially please. So I was just joking that if you don't like the diagnosis, you can always ask, really, do I have cancer? And it will say, okay, you may not have cancer for the following reasons. And it's a very plausible completion.
Yeah,
Given your prompt, because you don't want to have cancer, I'll tell you a possible world where you won't have cancer.
exactly.
so,
Yeah, these things are very good at taking cues. And the point you mentioned just about we shouldn't take what they are saying to us as evidence of what's going on internally is really important, and something that I worried about too. Another aspect of this I'm curious how you land on is one way to maybe get some more information on what the representations of a system could be, or the types of representations it's using, is something that came up in a conversation I had with Tal Linson, who basically asserted that you can constrain the types of representations a system must be using to perform a task if you're very careful about what the task is itself. So for example, if you're asking an LLM or something else to do something like reverse a list, even if technically at the bottom level, the representations are distributed in nature, at some level of abstraction, you could see that it must be using symbolic representations at some level of abstraction, because otherwise there wouldn't really be another way to solve the problem. And I'm curious if that's an intuition you agree with, or maybe where you fall on that.
So my sense is, first of all, I mean, I have very, very, very hard time agreeing with any claim that there is internal reasoning other than predicting the next token based on the previous tokens. And all you can get is you can provide extra tokens such that the context table CPT changes, and so they're more likely to tell you the things that are more relevant to you. I mean, the evidence about that is increasing as we speak. I mean, like, two of the most interesting things that I keep repeating these days is the thing that Tom Griffiths and co showed, where, for example, ciphertext, GPT-4 does ciphertext decoding, but it only does it well for 1, 2, and 13, because that's the data that is present in the common crawl. Because we tend to use either 1, 2, or 13, because rot 13 was a very common thing. And similarly, the muffins and the chihuahuas thing, that's been put to rest recently when people said, computer vision is solved because the muffin chihuahua puzzle, which computer vision systems were failing at, GPT-4 vision is able to solve, and some kid basically changed the order and it fails completely. So there is increasing reasons to believe that there is no reasoning. It is retrieval, the right retrieval at the right time. And we will always be impressed. I mean, my thing is that when we are interviewing people, if they answer a question, you assume that they have done it by reasoning, but more often than not, they may have prepared for the interview. They might know that, these are the kind of questions that come in the common things. In fact, that was one of the reasons why you can't actually ensure that people are reasoning as against just regurgitating something that they have heard before. And coming up with new questions that will force people to reason becomes harder and harder, in the context of standardized exams. So my way of looking at why GPT-4 does well in standardized exams is standardized exams have standardized question banks. And whereas, and so with that, they're able to actually, come up with answers that are, in the distribution that they've been trained on. Now, coming back to the other point that Tal Linson, you said, was pointing out, I have a slightly different way of looking at it, which is the prompt can force the LLM to structure its retrieval to fit a certain pattern. And in doing so, it is less likely to generate come up with wrong retrievals. That I completely agree with. Okay. So I think that, but then it's, again, you're not making it do reasoning. It's just you're telling it how to format its output. And one of the very deep results, actually, I was just talking to somebody a couple of days back, is there's this notion of syntax and semantics of a language and the distance between them. If I kind of not something like natural language, they're pretty far away. Okay. But as you make things more and more formal, the difference, the distance between syntax and semantics, roughly speaking, it can reduce. So that's one of the reasons why, if you are asking LLMs for an answer try to ask for it in code form, because one of the advantages is code has to be structured more than language has to be. Already LLMs cannot do syntactically incorrect English, and all syntactically correct English can still be completely far away from the semantics of what was intended. Code, on the other hand, when it generates the code, correcting the syntax errors with, for example, the incremental compilers, might get the corrected code somehow be closer to the semantic intent. And that is the way you can start seeing improvements in performance by the end user's perspective, because by constraining the language, you are essentially saying, you're reducing the possibilities, the measure of the incorrect generations by constraining the language. And that's true for code, and that's also possibly true for saying, write your answer in this following format. Code is a particular format to begin with.
Yeah.
Right? There is old work by people like David McAllister. I was actually telling somebody about this. There's a JSCM paper on taxonomic syntax and semantics, and there's some of these kinds of languages where the distance between the form and content is smaller. And that becomes actually good for you. We don't use that because natural language is great because it has full expressiveness. These other kinds of things sometimes might actually constrain you into saying things in awkward forms, and sometimes they might also have lower expressiveness, but they might have better connection, better connection between syntax and semantics. I would think about what you said in those forms rather than somehow saying prompt is changing the way it is reasoning. Prompt is changing ultimately just the CPT, and the CPT basically might generate a version of the answer in a different format, and that other format might likely have lesser chance of basically being incorrect. It's more possible ways in which actually there's an old joke that I'm trying to remember. There's this Irish proverb that says something like let everybody be kind of, whoever comes into this bar, may God make sure that they think that they do us good, and if they think of us in good way and they do us good, and if they don't, then basically they change their mind, and if God can't change their mind, then God should turn their feet so that we can tell by their walking, whether or not they actually are they're well-wishers or ill-wishers of you. In a weird way, you are changing the syntax into semantics there by far to the semantic intent. That's the kind of thing you might wind up doing in this prompting process. And sometimes that could be useful. And sometimes asking them for a higher level outputs, such as give me the code for the problem rather than the answer for the problem, is interesting. So actually, just something that's like fresh off the presses. I was having this conversation yesterday evening with my students. You talked in the beginning of the thing about mystery domain, where you change the words. Then, for example, the LLM cannot actually solve the quote-unquote box-fold problem. So they asked LLM, that same LLM, GPT-4, if take this mystery domain and try to think of an analogy for this, that makes it look like some other domain that you know of. Okay, and funnily enough, this is actually, it's not yet written, and this is like something that they were just talking about. And so funnily enough, GPT 3.5 basically comes up with far-fetched analogies, and GPT-4 apparently came up with Bloxworld as one of the top analogies. The funny thing is, it knows that this thing is actually like Bloxworld, but when you ask it to solve it, it still is making mistakes. So it's the issue of your right hand not knowing that you have a left hand. Okay, because each of these are different pieces for the LLM, and we can leverage this. In fact, if I want to make it solve the mystery domain, I might essentially make it construct the analogy first, double check the analogy, and then use it with respect to use that to make it actually solve the problem. So then its guesses will improve, essentially. So that is something
I think you're right.
sort of mind-blowing.
Yeah, I think you're right. And I guess what this brings up for the point that Professor Linzen made is I think the insight maybe doesn't cleanly translate over to LLMs, because the insight I was thinking about really, I think, was initially in the context of recurrent neural networks, where he was sort of talking about how RNNs show regularities, and they might implicitly compile symbolic structures into these sort of tensor product representations, and the way that these systems, maybe a little bit earlier on, they again might be using distributed representations at bottom, but they kind of can implicitly be seen as symbolic in some sense. And so I'm having trouble recalling the exact details of our conversation in this regard, but I think maybe there's like a slight difference there. But I think to what you said about large language models, the fact they are not doing reasoning and things like this, I totally agree with that. I think he probably would as well. But I do think maybe the representation insight perhaps is something that, I don't know, do you think that there are sort of other types of models, and we could kind of constrain
I completely agree. So when people ask, first of all, when people, after hearing that LLMs can't reason, then they try to say, do you think AI systems can ever reason? I said, what do you think AI systems were doing up front? They were doing reasoning. Essentially, it's not like reinforcement learning is reasoning, planning is reasoning. It's like, so the question is, first of all, in a modulo setting, LLM plus these verifiers can do reasoning. And secondly, there are people like Jan, for example, and LeCun talks about these JEPA architectures, which is like trying to learn. So trying to train the models, going a little bit away from just simple transformer architectures that are only trained to predict the next token, which is basically what we are currently doing, and hoping for miracles from that. Eventually, we will start looking at other architectures, and then that point of time, all sorts of interesting things can happen. In fact, currently, you can already see that you can put LLMs with a deep reinforcement learning system, for example, or a deep reinforcement learning system working off of a simulator, which, as I said, is actually a planning system, as far as I'm concerned. These two together are both based on neural networks and can do both generation and reason together. And the real question is, can you kind of marry it in such a way that some GPT, 15 RXW will essentially wind up doing both of these together? That remains to be seen. But I have no arguments that that cannot be done, because you already have one proof that these loosely coupled systems externally, they can already do both generation and reasoning in this LLM modular setting. And still a question of, if you want a single system, I mean, one of the best ways I think is, to me, LLMs are system one. It's basically system one in a different way than our system one is, but they're essentially system one. And it's not like they take any more time for a costly, complex problem versus a simpler problem. And the interesting part is because humans tend to use their system one to answer, like in general, it's not surprising. This is one of the things that people ask me about this blocks world and mystery domain. Humans are much better off in solving blocks world problems than they are at solving mystery domain problems. And then these guys will say, look, looks like LLMs are doing the same thing. They're no different from humans. And I'll say, no, not so fast. If you incentivize humans, they can solve the mystery domain problem. You cannot incentivize LLMs because there is no system two for them. They can ultimately all you can do at best is do fine tuning on this very specific domain. And so that then the reasoning again becomes a retrieval problem. Okay. But humans already can, essentially, if I give you the mystery domain in the PDL form, upfront, they may not, we don't feel like doing it. But I'll say, look, your grade depends on it, or you'll get $10 if you do this. They will solve it. Okay, because they actually have, and in fact, that's part of the whole thing about Russell's, people would rather die than think, and many do. We don't like using system two too much. That's why we try to follow recipes, but we do have a system two. LLMs it's not that they're not interested in using system 2. They don't have the system 2 competencies at all. And that has to be put outside. The verification, the reasoning, etc. competencies currently have to put outside.
Currently. Yeah. Another point you make relevant to this is the way that system 2 knowledge can more or less get compiled into system 1 knowledge. And so if we're thinking about a system that's like an LLM hooked up to something like an external verifier that serves as maybe a system 2 module, do you see a way for that to then get compiled into system 1 knowledge?
That's very much possible. That's again very much possible. In a sense, that's actually a very nice point. In fact, I have this whole picture, one of my tweets, making the difference between system 2, system 1 of human metaphors versus just if you see LLMs as system 1, what would it look like? And one of the interesting things is human system 1 has both things that cannot actually be compiled from system 2, because the stuff that is just built in for us, and also many things that we memorize. That means after you solve a problem, you remember the answer. So next time around, you don't have to solve the problem. Yeah. And so, in fact, if you misremember, and if somebody says, no, that's not the correct answer, you can always go back to system 2 and then debug it. This is actually the reason why it is indeed the case that people are bad at generation, but good at self-correcting. And because we do anthropomorphization, we assume LLMs can do that too. But LLMs can't, because LLMs essentially, basically do not have any additional competency in doing verification separately. But as you said, if you have an external thing which is actually solving, which is finding out the errors, etc., this eventually can become extra data on which LLM can train, basically it becomes part of the common crawl data, extended common crawl data. In a weird way, I would argue that, remember the Gato system that not too many people talk about, the Gato system that DeepMind did, that's pretty much what they were trying to do. They essentially, there is an agent with a simulator outside that was actually generating feasible behaviors. Okay, and what LLM is doing is it's looking at this behavior. Everything is a sequential thing. So behavior is a sequential data structure. It's also basically can be trained on predicting this sequential behavior. And it would do slightly better that way. In fact, back in 2016, way before LLMs, we did something very similar in AMAS 2016 that's actually got like a best student paper nomination, which essentially does the same thing where you get, instead of starting from planning domain model and doing planning from scratch, you can generate with a domain, with a sound planner, you generate a huge number of plans for many, many different goals. And these are all essentially sentences written in terms of the vocabulary of actions. Right? A plan is a sentence in the vocabulary of actions. And then we basically train an RNN to predict sequence completion task. And then at that point, we can then show that if I give you an arbitrary sequence with missing actions, it can actually complete, it can suggest to you what should be the actions that are missing, what are the actions that are missing. And if the actions are missing in the middle, that it's filling the holes. If the action is missing at the end, that is actually just doing token completion, the sequence completion. And that's not surprising that it can be done. Again, it's going to be an inductive task, so it'll never be completely guaranteed to be 100% correct. But that is the fine-tuning that will certainly help if you have this sort of external domain models. And so over a period of time, some of that can indeed come into the generator. And that sort of closes the loop on the Minsky hope that the generator can become slightly better over a period of time, even in this LLM modulo architecture. And normally, that's actually what happens. The phrase that I use, LLM modulo, it comes from SAT modulo architectures. Boolean satisfiability solvers basically are only good at doing Boolean true-false propositions. Many constraint programming scenarios not only have logical constraints, but also have like numeric constraints, linear constraints, quadratic constraints, etc. So what they would do is they would have the SAT solver come up with the SAT part of the assignment, which will then trigger other constraints for these other numeric and nonlinear solvers, which will then say, are we either happy or no, change the following thing. And then this becomes a modular loop. just like backprompting that I'm talking about for LLMs. And all those architectures, eventually they try to kind of do this no good learning. That means trying to reduce the number of the word no good basically is this particular sub assignment is no good because some critique or other would be unhappy with them. So instead of actually generating it, you don't generate it. And in fact, people like Rena Decter, I mean, my own old work, this is actually connected to explanation-based learning, the stuff that we were talking about in the beginning of the talk, beginning of the conversation. Because no good learning is it's actually learned in the hard way that this particular sub-assignment won't work. And then it can memorize it. And that way it becomes a better generator. And your idea that you were mentioning and that we were just talking about, which is external solvers critiquing some stuff, and then basically remembering that this particular thing seems to have this criticism, so avoid generating it, or at least use this as corrections data. In fact, one related point that I should bring up is everything ultimately for LLMs is based on the training data. Okay.
Yeah.
And because they're not doing reasoning. So to generate the solution, they use essentially correct data, that they have been trained on, and they are trying to generate the solution. To verify a solution, they can't do it by themselves. But if you have done corrections data, that means if part of the common crawl also included corrections data, that is the usual types of ways people make mistakes in coming up with solutions, it can use that. Do you see what I'm saying? And so this actually becomes a useful thing. And normally, we don't put as much knowledge on the web about corrections data as we put about correct data, which is why LLMs actually are not any better at verifying themselves, because they don't have any data to do that. And so we actually have a paper, that we have in the ICML KLR workshop last year with this undergrad, Daman in IIT Delhi, where we basically show that you can essentially, while LLMs by themselves are not any better verifiers than they are generators, if you are fine-tuning the LLMs, right, you can do fine-tuning in two phases. Suppose you have a huge number of plans, right, that are correct for this domain. You can basically, normal way of fine-tuning is just add that to the generative part of the LLM so that it will try to generate the correct token next correctly. The second thing that we do is you'll realize that these are correct plans. And so if you make random changes to this plan, they're likely to be incorrect. And so then you can train the LLM also as a discriminative classifier, which can actually look at the data and a plan and say it is right or wrong. Not showing the errors, but at least it learns to say. And we all know that sample complexity, the reason discriminative classification has become more popular in the beginning times is because they have lower sample complexity. You are not learning the full joint, you're only learning the label given the data. And so the same amount of data that you collected goes longer way in improving the discriminative capability if you actually train him to do that. And so we do this, this kid does that both to do the verification as well as to the generation. And that way we can actually show that fine-tuning can in fact improve, its self-critiquing capability. Because you specifically trained it on corrections data rather than correctness data.
Yeah, this is really important. And I think it ties to a pretty recent paper that I've seen about the generative AI paradox, which I think is making this sort of claim in the context of generation versus discrimination. And I think this was a bunch of people at the Allen Institute and maybe some other places, but largely Allen. And what they found was essentially that unlike in humans, for us often, I think, to generate things, we do need to develop some prior understanding of what's what and how things work.
This is agent choice group. Yes.
Yes.
And this is basically the point. This is more recent, and the stuff that I'm talking about is 6 months back, and I'm in the same wavelength. I basically, I'm a lot more in similar wavelength as the agents group. She used to be a lot more of a fan of LLMs, but she's become a lot more skeptical. And I don't think we disagree too much on the right way to look at LLMs. So they're amazing, but you should know these kinds of pieces that essentially what is hard and easy for humans and LLMs are not connected. And that's part of one of the things that study shows, the generative versus discriminative paradox. You might actually generate without knowing whether it's correct or wrong. And so you may not be able to. People normally don't have this issue because normally they actually, people also have it sometimes. If you mug up for an exam, that's how I catch you. Do you understand what I'm saying? If I'm feeling particularly sadistic and I know that a student has mugged up and they didn't understand, then they give the right answer, you ask them to explain. I mean, unless they have also mugged up the explanation. Right? And again, the problem is ultimately for humans, I can do some of this cross-examination and figure out. But one of the things about petabyte memory systems is it becomes harder and harder to come up with these diagonalization questions that will show that they don't have certain competency. Because the ability, you can essentially fake reasoning by just retrieval. And it becomes at a asymptotic level, it becomes extremely hard to tell. In fact, one of my other things is people tend to, when we tend to think in terms of logical reasoning, people normally talk about base facts are given and the theorems have to be proved from the base fact. And so if I just give you the base fact and, like, for example, I say, give the base facts and I say, is this following thing true in mentally or by systematic search, you have to do the theorem proving, right? This is true for humans most of the time. But first of all, even for those humans, if they happen to know that question that you would be asking, they would have known whether or not it's going to be following. And so they just regurgitate it. For LLMs in the common crawl, it's not like you're only having base facts. Common crawl is full of both base facts and deductive closure. That means things that follow from the base facts.
Yeah.
And we will be impressed that they can do this because, I mean, one of my other points is that in general, there's this, we really think that we know what's on the common crawl and we don't. And that's part of the reason why, like when Palm came along originally from Google, right? One of the big things was it could explain jokes. And everybody was blown away. Oh my God, how can it explain jokes? Well, it turns out there are websites that explain jokes for humor challenge, such as mine, and so there is all sorts of websites with all sorts of information. And so there are a lot more things that can actually be done by approximate retrieval than we normally assume, because we assume that, LLMs are working the way people are working, but they are not trained the way people are trained, and they are not working the way people are working. But they're very useful, but we should keep that difference, I think.
Yeah, that makes sense. I think maybe a good place to come to a last section here is sort of prompting based off of this blog post you wrote last year about AI as an ersatz natural science. And you said a couple of things in there that I found really interesting. One of them was and I'm quoting this, you say that AI is straying firmly away from its engineering roots, which I find an interesting way to put it, because I think at the same time, I see a lot of people right now, and I suppose this is more industry people who are really excited about LLMs, saying that engineering is sort of the core of doing AI research now, even more so than before. But my sense is what you're thinking about when you say that is that we've trained these massive systems and then we're kind of observing capabilities and developing understanding. But I'd love to hear you elaborate a little bit on how you think about all of this.
I think, thank you for bringing that up. I think that's one of the important things that I keep talking to people about. By engineering, I mean, specifically, the whole point of engineering is providing robustness guarantees. Okay, I mean, there are two different kinds of engineering. We were building bridges before we understood strength of materials. I mean, Romans didn't wait for strength of materials, textbooks before they build bridges. But then they just hope that they'll stand, and sometimes they'll fall, and they'll hope to try to do something better. The normal current quote-unquote engineering practice in the engineering school is you actually provide guarantees, which is why you can sue the person who built a bridge if the bridge collapses, because they're supposed to have given that. And AI was like that, essentially, in the sense that's part of the reason why I was talking about the fact that with expressiveness, the worst case complexity increases. And so you would avoid trying to do these more expressive problems because providing guarantees for them is computationally costlier. Whereas now we have strayed from that to, look, it works. What else do you want? Okay. And the problem with that is that's exactly what Romans were doing. I mean, when the bridge collapsed, it's not like they got to kill, they got to sue anybody, right? You should be happy that you have a bridge, But nowadays, we are no longer happy that we have a bridge. Bridges can be built. I want it to be built to the code to make sure that you followed all the current knowledge that humans have so that it doesn't arbitrarily collapse. I mean, again, truly, I mean, it's like very impressive that we can build these. I mean, you could say, I built you a multi-story building, you should be happy that it is there. But I still will sue you if in fact 6 months later it collapses. And that's because you did not provide any, in some sense, you are not able to provide any guarantee, right? I think that's the part I was talking about in the context of the AI becoming ersatz natural science. We did not engineer LLMs to have any specific capabilities. We engineered them, quote unquote, to predict the next token. And then we started saying all of this is emergent. Now it is able to, it has this emergent capability of telling jokes, emergent capability of guessing plans, and so on. And the problem there is you need to be careful in evaluating such claims. You have to be systematic. So my other way of saying it is, we all become sort of zoologists, and we don't have the statistical rigor that they use to kind of say, I mean, like a new animal has been shown and you're trying to see whether or not it can do various things. And you can't just go by one or two examples. You actually have to provide like a, systematic evaluation. That sort of was one of the things that happens in this whole planning thing. People actually can provide back prompts to the LLM, and they are essentially getting it to the correct answer, and they forget that they helped. It's something that you should do if you have a kid and you're trying the kid to do the problem correctly. You kind of help them along, you provide them hints until they do it right. But you don't think that somehow the kid did it all by herself or himself. You actually helped, and it was a useful thing for you because you're trying to teach them. But when you do the same thing with LLMs, you think LLMs did the problem and I'm just doing prompting. No, you're not just prompting. You're actually giving the hints. And this can only work if you know the answer yourself. If you are, otherwise it'll be blind leading the blind. And so one of my, I joke around that one of my biggest contributions to quote unquote Twitter science has been this meme that I posted of this complex mechanism about LLM reasoning capabilities, which all depends on this shaky foundation of human prompting, knowing the answer. And if they don't know the answer, you don't know when to stop reprompting the LLM. And that's sort of the kind of thing I was talking about in that ersatz natural science thing, in the sense, sometimes you do want to just study these artificial organisms like LLMs, which is fine, but you need to be careful and you need to use different kinds of evaluation techniques than the ones that you use for computer science. So for example, if you write a sorting algorithm for computer science and you proved that it is O(n) square complexity, you don't have to then also draw a curve showing it is actually only growing at n square level because you have proved it. You can't prove anything with these LLMs. So you actually have to do this curve. You need to give 500 different planning instances and seeing how often is it correct without you getting involved in trying to correct it, which is all we did. And then you suddenly see that it actually does much worse than people tend to see when they're doing one-on-one thing, because you tend to conflate what you are doing with what LLM is doing. If you don't conflate, they are great assistants. In fact, one of the best uses for them is, for example, if I'm writing an essay, I'll ask it to write an essay. I look at it and say, no, change this paragraph, change this other paragraph, and it does all this stuff. And then I look at it and say, I'm happy, I'm done. And I reduce my time. That's what it did for this doctor who writes her case studies. It reduced her time, but she knew whether or not the final thing that she's signing off is actually the kind of case report or the essay that she can be happy with. She didn't necessarily think that somehow LLM solved the generation problem or the report generation problem. So that is the kind of rigor that we need. Then we can use them because they are very effective idea generators in my view, and because they've been trained on essentially our collective quote unquote internet wisdom. And my bigger worry actually on that is that I keep saying that we should have the current snapshot of the web stored somewhere in that Norway seed bank, because eventually the web will be full of stuff that LLMs generate. And it's already being shown, and several people have already shown that if you retrain LLMs on the stuff that they generate, quality falls down, right? Because it's not like the usual idea of, semi-supervised learning with unlabeled examples, where the unlabeled examples, the entire example itself is real. It's just the label that is missing. Whereas if LLM generates an entire new story or a new case report, it's not at all guaranteed that it is actually as quote unquote real as the ones that it's been trained on. And so at some point of time, the web crawl will be kind of pretty badly corrupted. And at which point, given that we don't have good watermarking techniques, and also there are commercial reasons as to why people won't necessarily allow their LLMs to be watermarked, because why would you sell, why would I buy your service if it would tell everybody that I use ChatGPT to write my essay? I have this thing that, people who rent a vanity car, the first thing they do is remove the Hertz plate from it, because they want people to believe that it's their own car. And similarly, you want people to believe that you wrote this text. And so watermarking is not really a real solution. So eventually, if you're not careful, web would be corrupted. And that's a more asymptotic issue. And the misinformation becomes a bigger issue. It's what people miss essentially is Google was way better in that aspect than LLMs ever can be, because Google at least had external orthogonal ways of evaluating the veracity of the information based on where it is coming from. Because the messenger and the message are intertwined. And if the messenger is unreliable, the message is probably unreliable. And so all the other signals, including PageRank style stuff, was very helpful for, actually kind of making more trustworthy information. When the LLM essentially puts things together, it's not clear which part came from where. And so, in fact, I argue that when people say data quality is paramount for LLMs to do good stuff, yes, I agree, but it also tells me that LLMs, that should tell you that LLMs are not like general intelligence. They are only dependent on the kind of things that you are training on.
Yeah. I think maybe a closing question here would be one other really interesting thing you said in this blog post, which was that AI's turn to natural science has implications for computer science at large. That stuck out as really interesting to me, and I'd be curious to hear you elaborate a little bit on how you think about that.
I think that's that was slightly tongue-in-cheek, but the point basically is that I make this joke that when I first joined as a faculty member, all my colleagues in CS department will say, oh, poor guy, you're working in AI. Couldn't you be working in a lot more interesting things like databases and software engineering, et cetera, et cetera. And now they all are telling me that they're doing AI too. Everybody is doing AI. To some extent, what that meant is, to the extent if AI becomes like the dominant paradigm and generative AI or anything based on like this sort of large learned systems become the dominant paradigm for every area, the whole issue of robustness and proofs, etc., become an important question for these other places too, because some of them are a lot more theoretical to begin with. What exactly does it, how does it change? So it's interesting that Terence Tao, for example, says he was able to improve his, in some cases, he was able to use ChatGPT to come up with ideas, which I completely agree, because in fact, even in math, it's understood that there are mathematicians who are founts of ideas, and there are mathematicians who are good at taking a single claim and digging deep down to prove it. A classic case is Fermat's last theorem, that he just wrote it on the margins, and Andrew Wiles had to spend like 20 years of his life to actually prove it, a couple of centuries later. Both are important. And so the idea generation, conjecture generation, may be helped by LLMs. But if in fact straying away from guarantees and straying away from the engineering roots, which AI has, if it gets into the other areas, that would be that would have very interesting consequences. I mean, in fact, I think, in addition to computer science, like even in medicine, for example, these guys are saying, oh, look, LLM can do nicer, like ChatGPT can give good diagnosis to people that people are happy with. And I was saying, wait until the first ChatGPT based malpractice claim hits the courts. Then I would like to know what is going to happen, because ultimately we are just, there's no guarantee. Then somebody has to eventually pay, and that's the robustness. That's why, like, you can't just build a building and say if it falls, if it stays, you should be happy. If it falls, don't complain. That's not the way we work. And so that's sort of what I was meant, have in mind, in the sense there, in general, there is this difference, especially in AI. I think I mentioned it earlier in the conversation, that there's this neat versus scruffy AI. When I was a grad student, the quote unquote symbolic logic people, etc., who will prove stuff, everything, that would be like the neat people. The scruffy people will be, look, it works. What else do you want? And in the middle, again, AI became a lot more neat. Originally, it was scruffy, then it became neat. And then, in fact, it was so scruffy that we didn't even want to use probabilities. And we generated our own random things like certainty factors, etc., which actually had major problems at the time of expert systems. Many people don't realize that AI researchers would not use probability theory because they felt that's not the way people do reasoning. We should just not use it, and they would just come up with random other approximations. We went from that to more neat phase where we actually depended on things with firm semantics, etc. But now we are back into a scruffy phase where we are essentially looking at, wow, these things work. Are we, we should be happy. And, I think it may just go that way, or it may also essentially, given the current civilization we have, and given the accountability issues you have, eventually there would be ways in which, this will be tamed down, and somebody has to give some guarantees, and, my usual thing is that when people say, well, people also make mistakes, I say, well, until you know how to put LLM in jail, the way you can put people in jail because they were made a mistake, don't tell me that people making mistakes allows machines to make mistakes, because that's a very different aspect. And giving guarantees and being responsible for your predictions is something that we take for granted in the civilization. And that sort of runs counter to, look, it works, why do you care? So that's sort of what I was referring to there.
That makes a lot of sense. And I think this is a really good insight probably to close on. So Professor Kambhampati, I really appreciate your work, and you left us with a lot of great insights and takeaways today. So thank you for being so generous with your time and speaking with me.
Thank you. Thank you, Daniel. Thank you.
Fantastic. Let's see. I think I can probably pause the recording here.
Yeah.
Fantastic. Okay. Well, again, thank you so much